So if you're watching this, odds are it's toward the end of the semester, right before finals. Or if you're taking the nursing chem, might be right before exam one. Either way, you're probably stressed out. Here's what I want you to do to kind of help that. I want you to go to wherever you go to listen to music, Spotify, Pandora, what's the new one? Tidal. That's it. Or do you still pirate music? You do that? Really? You'd rather trust a website with 15 different download buttons than just do a simple Spotify subscription? Either. Anyway, just go find the soundtrack to the Jungle Book, Jon Favreau, the new one, the live action one, and just play Christopher Walken's version of I Want to Be Like You. It will make all your troubles go away, if not only for 3 minutes, but still, it'll be worth it. I promise. Because I can't believe they actually did that, because earlier in the movie, they did the blues song, but that one kind of made sense with the whole, what was going on in the moment. But King Louie in the movie is like this giant ape and really imposing. And I thought they're not going to do that song. They're not going to do it. But right as him and Mowgli are talking, you hear the drum below it. And I thought, are they actually going to play it? And sure enough, a minute later, Ooby-Doo, I want to be like you. Ooh. And I've never been more happy to be wrong. It was just, I want to be like Cub. It's awesome. I don't. If nobody has done a mashup with that song and that one video, Fatboy Slim, where he's dancing around the wherever, I am going to do that as soon as I'm done with this. It has to be out there somewhere. It has to be. If you've thought of it, odds are it's already on YouTube. I've learned that through the years. Or Twitter. Everything you've said has already been said on Twitter 1,000 times. So, might as well just keep it to yourself, right? No? Okay, whatever. Nuclear chemistry. For General 2, a lot of people will talk about nuclear chemistry at the end of the semester. And because most textbooks, they'll have like 4 or 5 extra chapters. There'll be one on organic chemistry and some other like deeper types of hardcore chemistry, like transition metal chemistry or whatnot. A lot of people like to do organic because a lot of those students are moving on to Org 1. But me personally, I've always liked to end the semester with nuclear chem because odds are that's probably the only place a lot of students are going to get any kind of discussion on nuclear science. And I think it's important because, when you think of the word nuclear, we all know what the first thing you think of is. But really, when you look at everything the field has done, the good has outweighed the bad by a wide margin. Yes, even if you count the 2 bombs that were dropped, still. So I like to talk about it a little bit. And one of the things we talk about are the different types of radioactive decays that can occur. So the first one that we'll talk about is alpha decay, which, if you know the Greek alphabet, kind of makes sense. That would be the first one we talk about. But with alpha decay, what is emitting from the isotope is a couple of protons and a couple of neutrons. So effectively, more or less, what you're emitting is a helium-4 nucleus. So an example of that type of decay would be americium-241. So when it undergoes decay, it spits out a helium-4 nucleus. So you're losing a total of a total mass of 4. So your mass is going to drop down to 237. You're losing 2 protons, so the atomic number is dropping down 3, which it's no longer americium anymore, it's neptunium. And going back to what I just said a minute ago with the whole good outweighs the bad thing, AM-241, it's in just about every smoke detector out there. So that is a product of nuclear science. It's like one of the first ones I like to bring up when people talk about, how the word nuclear is bad. But going back to this reaction, notice that like chemical equations, nuclear equations can be balanced. Did I say nuclear weird just then? I don't know. Anyway, with chemical equations, you got to have the same number of each atom on both sides using coefficients. But with a nuclear equation, notice that the total mass on the left side equals the total mass on the right. And on the bottom, the total atomic number on the left equals the total atomic number on the right. 93 plus 2 is 95. 237 plus 4 is 241. Also, one other thing. The resulting isotope, the new one that's formed, that's often called the daughter isotope. So Neptunium-237 would be the daughter isotope of the decay of Americium-241. So the second one we'll talk about is beta decay. And with beta decay, this one's a little weird because you're emitting what most people will call a beta particle. But a beta particle is basically something with the mass of an electron and it has a negative charge. So if it barks like an electron and it wags its tail like an electron, then it's probably an electron. So I just go ahead and call it an electron. And this is the symbol some people often use for electron or a beta particle, 0, beta, -1. Or I just like to use an E for electron because that's essentially what it is. There's another reason too, but I'll tell you that in a second. So that's weird. So something gets emitted from the nucleus that up until now you were told was somewhere else in that atom. Also, another thing is that when the decay occurs, the daughter has the same mass, but the atomic number has gone up 1. So how do you explain that? And for a chemist, we like to explain it by just sticking with the subatomic particles as much as we can. Because here's a secret about chemistry, and we could care less about quarks or bosons or ferrons or head-ons. Apply directly to the forehead. Bosons, one of those maybe not be a real thing, but that's okay. I'm thinking there's another on I could have mentioned. No, nothing. But yeah, we don't really care about quarks and all that crap because why? Until we have a reason to care about up quarks, down quarks, everywhere quark, we don't care. So again, and for a general chemistry class, we really don't care. So we try to keep it, as general as possible because that's the name of the course. All right, but anyway, back to where that freaking electron comes from. So based on what you see, one explanation that works is that essentially what's happening is that a neutron is being converted to a proton, and it does that by emitting this beta particle. And this is how we often show the isotope symbols for, I guess, all 3 subatomic particles now. I already mentioned electrons. Protons are usually 1p1. And, because the mass is 1, the atomic number is based on protons. So that makes sense. Neutrons are usually 1n0. Because the mass is 1, it has nothing to do with atomic number. And here you can see why we picked -1 for the electrons Z in our little AXZ symbol. Because doing it this way, our equation is still balanced. 0 plus 1 equals 1, -1 plus 1 equals 0. So that's why we write the symbol of an electron that way in these types of equations, for the whole balancing purpose. So the electron / beta particle is emitted, and since you're converting a neutron to a proton, they effectively have the same mass, so the mass stays the same, but you've gained a proton, so that explains how the atomic number is going up 1. So, for example, gold-201 is known to undergo beta decay. So it'll spit out an electron / beta particle. As far as what the daughter isotope is, Again, it's got to stay balanced. So the mass needs to be 201. And if the atomic numbers are going to stay balanced, something plus -1 has to give you 79. That would be 80. And be careful and don't say 78. It's really easy to go the wrong way. But yeah, atomic number 80 is mercury. So next we have gamma decay, which again makes sense if you know the Greek alphabet. The next one isn't delta decay though. Maybe it should be, but anyway. I guess they decided to go in Greek after the first three they discovered. But with gamma decay, you're releasing gamma energy, which is very high frequency energy, way up there above X-rays and UV radiation. And an example of a gamma decayer would be technetium-99. So it releases gamma energy, and the way we write that in a decay equation is we use the little Greek letter gamma with a 0 and 0 as the mass and atomic number. And if all you're doing is emitting energy, nothing's really changing about the atom except how much energy it has. So it's essentially the same isotope as before. But this can look kind of weird, and sometimes you want to distinguish between the daughter and the original pre-decay version of the isotope. So what you'll often see is a little letter M after the mass number. And the M stands for metastable. It just means that it has more than one form of energy, or it exists in more than one form of energy. So if you ever see a little M next to the mass number, that just means that it's a gamma decayer. And actually gamma decay follows pretty much all the other decays that we talked about, because when you're messing with the nucleus, converting a neutron to a proton, spitting out alpha particles, the nucleus is going to have to rearrange all those little subatomic particles, and when that does, that takes energy, and it's usually in the form of gamma energy. But in Gen Chem, we usually just treat it as its own separate thing, and we don't worry about what I just said. So don't, unless your teacher tells you to. If I'm your teacher, then don't worry about it. But next, we have positron decay. And it's called positron decay because what is emitted is a positron, which is basically a positive electron. So the way we often write its isotope symbol is 0 beta plus 1. Although I don't like that in a Gen Chem class, because you see the beta, you think beta decay. So I like to use the E in my classes. And so an electron, we write 0e -1. A positron, a positive electron, we just 0e plus 1. And a positron is it's a form of antimatter, and I won't go into all of what antimatter is, but if you're on YouTube, if you go search for that next, you'll find a lot of hits on what antimatter is. Before we talk about how this weird new thing spits out of the nucleus, what happens to the daughter is that it has the same mass, but the atomic numbers drop down 1. So all of this sounds like the opposite of beta decay. Beta decay, you spit out an electron. Here you're spitting out a positron. There, the daughter, the atomic number went up 1. Here it's going down 1. So if everything is opposite, maybe it would make sense if the conversion was opposite. So what I mean is that instead of a neutron being converted to a proton, maybe here a proton is converted to a neutron by emitting a positron. And that's the way we usually explain it in Gen Chem. That way the mass stays the same, and since you're losing a proton, the atomic number is going to drop 1. So an example of a positron emitter is copper-60. So you spit out your positron. Again, the equation has to stay balanced, so the mass is going to stay 60. 60 plus 0 is 60. The atomic number must be 28, which is the symbol of the atomic number of nickel. Also, as a side note, one thing that I will go ahead and tell you about antimatter is that when it collides with matter, they basically cancel each other out, and matter is converted to matter. The antimatter is converted to energy. So when it leaves the nucleus, the first type of matter that it usually sees is an electron. So those two particles will collide, and the result is a couple of equivalents of gamma rays, which is how a very common medical diagnostic tool works, known as positron emitting tomography, or topography. Can't remember. Tomography. I think it's tomography. If I'm wrong, then I'll flash it here and call myself a dummy. Or the shorter way to say it is just PET scan. So the last one we'll talk about is called electron capture. So like the name implies, an electron is captured or absorbed from one of the inner shells, probably the first shell, n equal 1. And it is technically still a radioactive decay because something is emitted from the isotope. In this case, it's X-rays, because when you remove that electron from one of the inner shells, say you remove it from the first shell, that leaves a gap in basically the electron configuration. So the electrons are going to have to reshuffle to fill in that hole and follow the Aufbau principle. Everybody's in the lowest state, in that ground state configuration. And when that happens, again, energy is released, kind of like we said earlier for gamma rays. But in this case, it's in the form of X-rays. So what we say happens is that electron is absorbed by a proton. And if you follow the mass number and atomic number, that should give you a neutron. So the overall effect is that the mass should stay the same, and we're losing a proton, so the atomic number should drop down 1. And if that sounds familiar, that's because that's exactly what we said happened to the daughter isotope of positron decay. But remember, the difference is what's actually emitted from the isotope. With electron capture, you're emitting X-rays. But with positron decay, the thing it's emitting is energy on the gamma part of the spectrum. But other than that, yeah, the daughters are converted to the same thing. So an example of an isotope that undergoes electron capture is gallium-40. So it works just like the previous 4 examples, only now the particle is on the reactant side since it's being absorbed or captured. Balancing still has to work here, so 40 plus 0 gives you 40. 19 plus negative 1 gives you 18, which is the atomic number of argon. So there you go. There's a little bit of nuclear chem. There's some other nuclear chem that I talk about, and I'll probably talk about that a little bit later, about how you predict decays and all that fun stuff. If I remember, maybe I'll actually put it on the little upper right corner where you see stuff pop down, which I don't use that enough because when I make these videos, it's like, okay, edit it, gone, gone, whatever. But anyway, I'll talk about some more nuclear chem one day. That'll be it for now. Bye. Ooh, ooh, ooh. I want to be like you. Ooh.